All right, welcome back to the lab session. So over here, we're going to use the same data set as we used in the logistic regression class to actually build the same naive Bayes algorithm, right? So we use this PIMA Indian data sets, right? We use this we use this when we're dealing with the logistic regression. All right, so we're going to use the same thing to make prediction whether a patient is having diabetes or not. All right, so we're going to use the same data set for this purpose. So for all the exploratory data analysis that we did in the logistic regression class is going to be applicable here. All right, so we are not going to go into that again because we've already done that. Okay, so loading the data set and then reading the data and doing all these exploratory data analysis, right? We did all of them at the logistic regression class. So I entreat you to actually look at that exploratory data analysis. We did a detailed exploratory data analysis to this data set. All right, so we are not actually going to go into it again because we've done it again. In the logistic regression class. So let's proceed and then see how we are going to implement our naive Bayes over here, right? So the same way as we did in the logistic regression class, we divide our data set into 70 30 70 for training and then 30 for testing. Okay, and then after that we are coming to split it, right? So we have our target, which is the class, right? And then we have the rest of the variables to be for X, that is from preg plus, press skin, test mass, pedi, age, right? So all these are going to be for S, right? Are going to be for X, and only the class column is going to be our target, right? And that's what we put here, right? So the same thing that we did in the logistic regression class, all right? And then after that, we split our data set, right? We split it into training and then testing. So just like we did in the logistic regression, all these steps are the same thing, right? Splitting it into 30 and then 30 and 70, right? 30 for training and then setting a random seed so that we get to the same random numbers over and over again as we run the code. Okay, then we are using the train test split over here to split our X, right? And then our Y. Okay, so as I said, we split the X and then some of the variables that we're going to use for training, we store it in what is called the S train. And then some of the variables that we're going to use for testing, we store it in what is called the S test. And then we do the same thing for the Y. Okay, the one for training in Y train, and then the part for testing in Y test. Okay, so just the same thing, right? And this one is just an overview, to see which variables have been randomly picked for training, right? For S train. So you can see that we have random indexes over here, right? All these are, we can see that the data points or the rows that were picked were randomly picked. Okay, so basically just the same thing over here. What we are going to be interested in, right? So over here you can also see the ones that have been put in the test, also randomly picked. Okay, and if we check this part, I actually wanted to show you that we have 70%, so 69.92, right? Of the data for training and then 30 for testing, right? So I pick S train divided by the total and multiply by 100. S test also divided by total multiplied by 100. That will give me that result. Okay, so just the same thing that we did in the logistic regression class, right? If you remember, there were some hidden values that were represented as zeros, right? So we did the NAN and we did not find any null values, but intuitively we realized that those patients that their tests were not available, they were actually represented as 0, right? So that's the same thing that we did here. And then we actually replaced those zeros with the mean, right? So we dealt with all this using the simple imputer, right? Using the simple imputer, we're able to replace the missing values, that is 0, with the mean of each of the columns, right? So that's basically what we did, and then store our column names over here so that later on we can use it, because if you do it right, they are going to lose their column names, right? As you can see over here, it's just going to give it a default column names. So in order for us to replace these column names that we have in our original data, right? So our original data is actually having these column names, right? It's having this preg flash, press, skin, test, mass, petty, age, right? So that's what it's actually having. So in order for us to get that, after using the simple imputer, it's going to lose that column names, okay? After you convert everything to a data frame, right? We want to replace those column names back, okay? So I mean, both of them, the S string and then the S test, they all lost their, they all lost their column names, okay? So over here, we are going to replace those column names back, all right? Then that's why you have it this way, okay? So the same detailed analysis that we did in the logistic regression classes, the same thing that we will do here before we start building our algorithm. So if you don't get anything of, anything here, I entreat you to go back to the logistic regression, just pause it for a while. It will just take you a few minutes to actually go through that, right? And then you get to understand each of these, right? We actually did exploratory data analysis for each of these things that you're seeing here in details, okay? And each of the interpretations over here with this one, we did everything over there. So I entreat you to go back there if you have not watched it. If you have watched it, I'm sure you are aware of everything over here, okay? So the main thing that we need to do over here is to build our naive Bayes algorithm. Okay, so now let's start by building an algorithm, right? So just like we did in the logistic regression class, we first import whatever we need so that which will help us to build the algorithm. So in this case, we're in sklearn, right? In sklearn, we want this naive Bayes, right? And then in naive Bayes, we are going to import this Gaussian MB, right? So the Gaussian MB is nothing but helps naive Bayes to assume, right? Helps naive Bayes to assume a Gaussian or normal distribution, right? So Gaussian is nothing but a normal distribution, right? So it's this Gaussian MB helps this naive Bayes to assume a normal distribution, okay? And this is because we actually want to estimate the mean and then the standard deviation of our data, right? We actually want to do that. So we actually use the Gaussian MB so that we will be able to assume a normal distribution. Now, as we did for the logistic regression, the same thing over here. As you import your algorithm, what you do is to initialize it, right? So initialize it to any model that you want, right? So in this case, we're initializing it to a model, a variable named as model underscore, okay? So, it's just a variable name. You could use any variable name that you want, okay? Now, after you initialize it, it just is more like giving the power that Gaussian MB has to this model over here. Okay, now after you initialize it, now what we're going to work with further on is this, right? Because this one is having everything that Gaussian MB is having now. All right, now we're going to use that to fit, right? To fit on the training data, right? So remember that we divided our data into 70% for training and then 30% for testing. All right, 30% for testing. So the 70% is what we are using here, right? So we are letting our model learn from, so fit here is more like learn, okay? You can think of it that way, to learn from the training, right? To learn from these training data that we have. Okay, so now if we do that, right, the learning has happened and now our model now understands the data that is inside here, right? It has learned from it. So more like you are giving a past experience to this, right? So making this model learn from the past experience. That's the past records that the company is having, right? The hospital is having that, which includes some features or some records that they collected with regards to the various patients, right? So that is what the model has already learned, right? So moving on, you can actually use this model that has learned from the past data to make predictions of the future data that will come in, right? That will be a future records that new patients will come in with, right? So now we will base on this past data to make predictions of this future data that will come, right? After our model has learned. So this is the only thing that we need over here for it to be able to learn from this. Now, after it has learned, it has become experience. So we can now use this one moving on. All right, so let's move on from here and then see what we can do over here. So now let's work with it. With the training data, it has already learned from the training data, right? So let's just feed it to the training data. If you remember, we talked about something called something called overfitting, right? We talked about something called overfitting, right? And then underfitting. Okay, so let's try and then see how we can fit that one inside here, or we can bring that one inside here. Okay, Now, if your model learned from the training data, we always expect it to be doing well, just like you are in your college, right? And so throughout the semester, you have your professor teaching you, right? So as the professor has taught you something and giving you all the lecture notes, and you have learned from the lecture notes, you will be, you are expected to do well at the final exams, isn't it? So the same way, we have already given our past data, right? Our past data to this model to learn from it, so we expect it to do well on that. Okay, so if our model is not doing very well on the training data, then we will say that it's underfitting, right? It was not even able to learn, right? Just like if a student learned from the professor and then all the lecture notes, and then at the end of the day, the student couldn't perform in the exams, we say that the student did not actually learn very well, right, during the learning process. Okay, so the same way, if our model if our model is not able to perform very well, then we can say that our model is underfitting, that is not even able to fit the training data, right? It's not able to learn from the training data better. Now, however, if it is able to actually do very well on the training data, right? So able to do very well on the training data, but performs badly on the testing data. Remember that I'm using two terms here. If it's able to do very well on the training data, right, and perform badly on the testing data, so that's going to be the S test, right? If we use the S test, remember that the S test is the data that our model has never seen it. Okay, so now this is the model that it has, the data it has seen it, right? So if it performs very well on this one and then performs badly on this one, then we say that it is underfitting. It's overfitting, right? Which means that it's memorized everything here. It has memorized everything. It's just like in your normal school, right? When you are able to memorize everything and then you get good grades, right, in your internal assessment. But when you go for external assessment, that is something that you have not learned before, something that you don't know anything about it, but you're going to use your internal experience to actually write that external exams, right? But in that case, you might end up performing badly because during the internal assessment, you memorize everything that the lecturer gave you, and the lecturer brought you the same thing in the exam, so you were able to pass. It doesn't mean that when you go for the external exams, those lecturers that don't know anything about you, those lecturers you have not learned from before, they will come with their own different perspective, their own different questions altogether. You might end up failing. Okay, so that is what is happening. So if your model is able to perform very well on the training data but performs badly on the testing data, then we say that your model is overfitting, right? That is, it overfits, right? So remember that we use fit here. So it overlearned from this data, right? And later on it's performing badly on this one that it has not learned from. All right, so let's try and then see how we can come up with this. Okay. Now you can see that when we use this model.predicts, right, we are predicting based on the training data, right? So since this one has learned already, right, it has learned already, if we give it the training data to actually make some predictions, right? So let me just let me bring the training data here. Let me print the head of it so that you can actually see, right? So if we see this as train, right, if we see this as train over here, right, this is what we have, right? So this is the data that we are given, right? This is the data that we're given. So our model, this model that we have, right? This is the only thing that we want. This model has already learned from this. So what is happening here is that given this patient, let's pick it this way, right? Given this patient, right? Let's say patient, let me even pick this patient. Let's say patient 2, right? Let's say patient 2. Now, if this patient comes in, right, don't forget all these are different patients, right? All these are different patients. So if this patient 2, right, comes to the hospital, and then we have these diagnoses, right? We diagnose, we do all these diagnoses. That is the pregnancy test, the plasma test, the blood pressure, the skin thickness, the test of, the insulin test, the body mass, right? And then the over here, there's the pedigree. If we get all these, right, and then the age of the patient, right? If we measure all these, right, we're going to have these data points for that patient. Now, can we make a prediction whether this patient is going to be diabetic, right? It's going to be diabetic or not diabetic. Okay. So now this model has learned from all these patients, all these many patients, right? So it's able to draw some patterns from that. Now, if we feed the data back to it, right? Now, if we see this 1, 0, 1, 2, right? So it is predicting that this is not actually it's not diabetic, considering the diagnosis that we did. This patient is not diabetic, so it's predicting this one as 0. Okay, so this is the only thing that we want. This is what we want to give to the hospital, so that when new patients comes in, they'll be able to make that prediction, right? Whether the person is going to have diabetes or not, and they don't need to do this manually again. They only need this model, and then subsequently they will just be feeding all this, so they can have diagnosis for about 1,000, 10,000 of them, right? Without explicitly saying that they will be having diabetes or not. They can feed all the thousands and 10,000s of the patient's records into this model, and this model will do that automatically for them. It will predict this for them. Okay, and that is what we want to actually do over here. All right, so this is we did it for the training data. Let's see the score of that, right? Let's see the score of that. Now, if we check the score of that, and don't forget I'm using metrics, right? I'm importing metrics, right? So in metrics we have what is called the accuracy score. So I'm going to check the accuracy score of the Y train, and then the train prediction that we did, right? So don't forget, when we did the prediction over here, right? This prediction that we did, we store everything in the variable called train underscore prediction. Okay, so that's what you can see over here, right? Train underscore prediction. This is our Y train, which contains our target of 0 or 1. So we want to compare it and then see how well it's matching, right? The prediction that we did, right? So you can consider this as the original zeros and ones that we have, right? And then this one is the new zeros and ones that we have. So we want to match them and see where zeros are matching with zeros, right? And then where ones are matching with ones. Okay, that's what we want to do over here using the accuracy score. So after we do that matching, then we calculate the score of that, right? We calculate the score of that. So if we do that, right? If we do that, let's see the score that we have, and see that we have 73% or 74% if we want to run it to 2 decimal places, right? So it's not bad. I mean, doing 74% accuracy is not bad, right? But if you want to put this into production, we need to actually go back and tune some certain things so that we get higher accuracy than this, because at the health sector, this is critical. Okay, if you're predicting whether a person is having diabetes or not, this is critical. We have to actually be sure that our model is performing better than 74. Okay, so let's see how well it will do. Remember that whatever we are doing it on the training data, right? We're doing it on the training data. So let's see it on the testing data. That is data that it never learned from, the data that it has never seen, right? So let's see that one. Okay, so the same way that we did here, we pass in the data, right? We pass in the S train, and then we made the prediction. So in this case, we're going to pass in the S test, okay, which is the data that he has not seen before. This is the new record of patients. So if we do that, we see what we have over here. So it's making predictions and saying predicting some patients as being 0, that's not diabetic, and predicting some of the patients to be diabetic. So if I print the S test also for you to see, remember that here I printed the S train for you to see, and then these are patient records that we have already. These are the patients that have visited our hospital, and we have their records. So if we come down here, right, these are the patients that have not visited our hospital, and we represent this test, right, test the data as patients that have not come to our hospital before. These are new patients, right? So we want to base on these new records, right, and then make some predictions. So if we see what we have in there, right, if we see if we see what we have in our S test, so let me just print at the head of that so that we can actually see. That is printing the first 5 rows for us to actually see, right? So dot head. All right, so if we do that, right, you see that this is what we have, right? This is what we have. So let's say these are new patients that came to our hospital, right? These are new patients that came to our hospital. So if we pick, say, the last patient, let's say patient 4, right? If we pick the patient 4, so this is the record that the patient 4 is having. We recorded the pregnancy, the plasma, the blood pressure, the skin thickness, the tests, right, and then the mass, the body mass, and then the pedigree, the age of the patient. So after doing all that, and then we feed this patient to our model, right? If we feed this patient to our model, right, now we can use the predict function to make predictions, right, with the help of our model, right? Now we can see that at 0, that's 0, 1, 2, 3, 4. Okay, so 0, 1, 2, 3, 4, right? We are able to predict that this patient is not a diabetic, right? This patient is not diabetic. Okay, so basically that's what we do. Even in production, right? Doing building the algorithm and using it to make predictions for future data that will come in. Okay, now what we're going to do, right, is to check the score of that, right? Remember that when we check the score on the training data, we got this 74. Now, if we check it on the testing data, you see that it's actually doing better, right? It's actually doing 77%, right? It's doing 77%. So, I mean, this is good. This is good, right? I was talking about this overfitting, right? I was talking about this overfitting and then underfitting, right? I was talking about these two, right? So now that our model is actually performing well on the testing data, right? We can actually see that we are actually under the, I mean, we also have the normal, right? The normal one that we want, that our model is able to generalize, right? Our model is able to generalize. That's what we want, right? However, if the score up here, right? If the score up here, if this score right, if this score was better than this score, then we could have said that our model actually memorized and it was able to do well on this training data, but not able to do well on the testing data. So in that case, we will say that it's overfitting, right? We will say that it's overfitting. But if it was actually even performing poorly, maybe like 30% or 40% over here, then we will say that it is underfitting. Okay, so but this one is actually doing good. Okay, it's doing good. However, we can still make it better. Okay, so when we get to performance measures and tuning hyperparameters, you get to understand what I mean by that. Now we can also use what is called the confusion matrix over here to actually get to know how many of the ones we predicted as one and how many of the zeros that we predicted as zeros and the wrong predictions that we made. Okay, so let's actually consider this and then see how well we can explain it over here. Now if you see this, right, this one I'm printing the title over here, as you can see over here, right, confusion matrix. Now I'm using this matrix, right? I'm using this matrix, and then in matrix we have what is called the confusion matrix, right? So confusion underscore matrix. Then inside that I'm passing my y test and then my y predict, right? So don't forget we did this over here, right? When we made the predictions, we store everything in what's called test predict. So that's what I'm using over here, right? That's what I'm. Let me push this a little bit up. Okay, so that's basically what I'm using over here. That is, let me do this, right? That's basically what I'm using over here. My test underscore predicts, right? And then labels, we have only one. We have one and then zero, right? We have only one and zero. That's whether the person is diabetic or not diabetic. Okay, and that's what I'm putting over here. Now, after doing this, right, I store everything in a variable called CM, which is confusion matrix, but you can use any other variable name that you want. Okay, now what I'm going to do is to convert whatever results that I'm having here into a data frame, right? I'm going to convert everything into a data frame over here, right? So I'm passing in my CM over here, right? And then I'm setting an index to be 1 and then 0. That's what you can see over here, right? That's what you can see over here, 1 and then 0. And then I'm setting my columns, right? My column names to be predict 1 and then predict 0. And that's what you can actually see over here, right? Predict 1 and predict 0. Okay, that's what I'm doing. So I convert everything into a data frame, then I store it in a variable called df underscore cm. That's the data frame of the confusion matrix. Okay, so as I said, if you're given a variable name, make sure that it makes sense to you so that when you encounter it anywhere else, you can actually identify it. All right, now I'm setting the size to be the figure size to be 7, and then 5, that is the length over here, right, to be 7, and then the height over here to be 5. Okay, so 7 units, 5 units over here. Now I'm setting over here, I'm using this sns.heatmap that's in Seaborn. I'm using the heat map function over here to plot this heat map, right? To plot this heat map. Otherwise, I would have gotten this thing that I'm having here. I would have gotten it in this way, 55, comma 30, right? And then I would have gotten this, right? And then 120, something like that. I would have gotten it in this form, right? But I want to plot it nicely like this. All right, so that's why I did something like that. Okay, and then here I'm using annote. That's something like annotation, right? Annotation equals true, so that I'll be able to see these numbers that you're seeing, right? I'll be able to see them. Okay, I'll be able to see. So basically, that's all for the code that here. So let's come to this one itself and then try to explain it, right? Let's come to this and then try to explain it. So let me clean everything here, and then let me shift this thing a little bit up, okay, so that you can actually see it very well. Now, what we are doing over here is that consider this one as the original, right? This is the original ones that I have, and this is the original 0 that I have, okay? And this is the ones that I predicted. This is the ones that I predicted, okay? So we have 55 plus 30, that is going to give you something like 85, right? It's going to give you 85. And this one we have 120, right? You have something like 120 plus 23, right? So that's actually going to sum up to 143, right? Something like that, right? This is here is 120. No, this is 23 rather. This is 23, and then this is 120. Okay, so 120 plus 23 is actually going to sum up to 143 over here. So that's the total. So this is the total ones. This is the total ones, right, that we have, and then this is the total zeros that we have. Okay, total ones. So let me just take it from the back. Total ones equals 85. Total zero equals 143. Okay. Now, out of this 85, right, I was able to predict, right? So if you see the prediction over here, right, and then the actual, right, I was able to predict 55 of them correctly as 1, right? 55 of the ones I was able to predict them as 1. Okay, 55 of the ones I was able to predict them as 1. However, 30 of the ones, right? 30 of the ones, if you want to extend it further, right? Let me change this one, right? Let me change this. Okay, 30 of the ones, right? 30 of the ones, I predicted 30 of the ones as 0, right? I predicted 30 of the ones as 0. Okay, so this one is actually a wrong prediction. Okay, so these 30 were supposed to be predicted as 1, but I wrongly predicted them as 0. Okay, and these if you see over here, this is like 1, this is like 12e plus 0 2, so this is more like this multiplied by 10 exponent 2, right? They're just going to give you 120. That's why over here I wrote 120 plus the 23. That's I wrote 120 plus 23, right? That's what I did over here. Okay, so basically that's what you're seeing. So over here, out of the zeros, right? Out of the zeros, I was able to predict, right? I was able to predict. Let me change this. I actually want this one. I was able to predict the zeros, right? 120 of the zeros as zeros, right? I was able to predict 120 of the zeros as zeros. So this one is a wrong prediction. I mean, it's a right prediction. Just like this one is a right prediction. Okay. And then out of that, right? Out of the 143, right? Out of the 143 zeros, I predicted I predicted 23 of them, right? So out of this, you see over here, if you consider it, so these ones were supposed to actually be predicted as 0, right? But I predicted them as 1, right? So these 23 were wrong predictions. Okay, these 23 were wrong predictions. So let me just take it one more time so that you get to understand it very well. So over here, right, I have this original one. Okay, I have this original one. Then these ones, right, were a total of 85. So I was supposed to predict these 85 ones as ones, right? However, out of these 85, right, I was able to predict 55 of them as 1, right? And then 30 of them as 0. So these ones, instead of predicting them as ones, I wrongly predicted them as 0. So that's what you can see where it is, right? These 30 of them, instead of predicting them as 1, right, I wrongly predicted them as 0, right? That's my prediction 0 over here. That meets this one over here. However, 55 of them, I was able to predict them as 1. Okay, the same way over here, the zeros, right? Out of the zeros, I was able to predict 120 of them. So most of the zeros, I was able to predict them as zeros, right? Most of the zeros, I was able to predict them as zeros. And then 23 of the zeros that were supposed to be predicted as zeros, I predicted them as one, right? Which is a wrong prediction. So you can consider this part, right, as wrong prediction, right? You can consider this part as wrong prediction, and then you can consider this, right? You can consider these ones as the correct predictions. Okay, you can consider these ones as the correct predictions. All right, so this is basically what happens. This is what the confusion matrix will help you to actually identify how many you were able to predict right and how many you predicted wrongly. Okay, so let's move on and see how we can also use what is called the classification report to actually derive same insight over here, right? but we can use the classification report to actually. So in the previous, the logistic regression class, we learned up to the confusion matrix, right? So in this class, we're adding the the classification report rather, right? We are adding the classification report so that as we progress, we will be keeping on adding some concepts for you and then explaining it so that you actually get to understand things clearly. Okay, we are actually going to take this as a separate class, but as we progress, we still be adding them so that things will be clear for you. All right, so over here, let's see what we can actually do. Right, let me get rid of this. Now what all right, so over here, let's see what we can actually do over here. Now, in matrix, right, I'm importing what is called the precision score, the recall, and then the F1. Okay, I'm importing what is called the precision score, the recall, the recall score, and then the F1 score. Okay, so let's see what these things mean, right? So over here, I'm printing the title over here, which you can see down here as classification report. Okay, and then in the matrix, right, remember that in matrix I can use what is called the classification report. So basically what you can actually do is that you can even ignore this, right? You can ignore this over here, right? If you want, you can ignore this and then just do this, right? Do this, right? That will also work perfectly for you. Okay, that will also work for you. Now I'm using matrix.classification report over here, right? I'm using that, and then I'm passing in my Y test and then the test predict and then the labels, just like I was doing it with the confusion matrix, right? Just like I was doing it with the confusion matrix. I'm passing in the same thing over here. Now if I do that, this is the result that I'll get, right? This is the result that I'll get. So let's try and then see what this result is actually telling us over here. Okay, let's try and then see what this result is actually telling us. So if you see precision over here, right? If you see precision over here, what precision is actually telling us is that out of the ones, we have 85, right? We have 85 of the ones. So out of these 85 ones that we were able to identify 55 of them as ones, right? How many of them were really ones, right? How many of them were really ones? Okay, how precise are we? That's what precision is actually telling us. So we can see that we were having 75%. At 71% over here, right? So precision is giving us 71%. So out of the 55 ones that we identified as ones, right? Because the total is actually 85, right? So and we identified 55 of them, right? If you see the confusion matrix up here, right? We're able to identify 55 of the ones as ones. Okay, so out of these ones that we're able to identify, how many of them were really ones? Okay, that's what the precision is actually going to give us, and we have 71% over here. And then if you take the zeros, right, we're able to identify 120 of the zeros as zeros. So how many of these zeros that we identify as zeros were really zeros? Okay, and that's what we can see, that we have 80% over here. So you can see that we are able to identify more of the zeros as zeros than the ones. Okay, so that's why I see 120 of them were able to identify them as zeros. Okay, that's what precision is actually giving us over here. Okay, that's the information that precision will actually give us, that out of the ones that we are saying that 55 of them we're able to identify them as ones, right? How many of them were really ones? That we got a score of 71%, right? And out of this total that we have over here, we're able to identify 120 of them, right? The zeros, we're able to identify 120 of the zeros as zeros. So for that, we have a precision score of 80. All right, so that is actually high, and we can actually see that we are able to identify the zeros mostly at the time, most of the time. That's why we have 120 of them as compared to the wrong ones that we did over here, which is 23. Okay. Now, if you take the recall, right? Now, what we are saying is that out of the 85 ones, right? And then we're able to actually predict 55 of them as ones, right? So how many of them are out of them? How many of them are we actually being able to recall? How many of the ones, right? The total ones, are we able to recall them as ones, right? How many of them are we able to remember them? How many of them, right? When we're talking of we, I'm referring to our model, right? I'm referring to our model. So how many of them is our model able to recall, or our model able to actually remember? Okay, so we can see that that record score is actually giving us 65, right? And if we see that the same thing for the zeros, you can see that we have 84% over here. So we're able to recall most of the zeros as compared to the ones, right? We're able to recall most of the zeros as compared to the ones. All right, and the F score here, right? The F score here is the weighted average of everything over here, right? That is the precision and the recall, right? It's actually the F1 or the F1 score, right? It's actually giving us a weighted average, right? It's giving us the weighted average of the precision. Okay, it's giving us the weighted average of the precision, right? The precision plus the recall, right? Plus the recall. So in this case, we divide it by 2. So if we take, say, 0.71 plus 0.65 divided by 2, something like that. Okay, and you're actually going to get your this thing, your F1 score over here. Okay, if you do the same thing for this, for the second one, for the 0, you also get the same thing over here. Okay, so basically that's what's the F1 score. So you can even ignore these two and then use the F1 score to actually make that general assertion over here. Now you can see that if we consider the F1 score alone, you can see that we have 67%, right? We have 67%. We are doing 67% on 1 when you consider 1 with respect to 1, right? And then we are doing well, or very well, on the 0, right? On predicting zeros, we are doing very well because we have around 82%. Okay, so we do very well to predict zeros, right? More than ones. That's why you can see actually we were able to predict 120 of the zeros as compared to the wrong predictions over here, and then we were able to predict only 55, right, of the ones as ones, and still making a lot of mistakes, right? We're still making a lot of mistakes in there. Okay, so basically that is what the classification report will help you to do, right? How well you are doing in predicting each of these classes. Okay, so we can see that overall, if we take the F1 score, you can see that overall we are able to do well, I mean around 67% in predicting ones as against 82% in predicting zeros. Okay, so basically that is it, and we will move on to the next project, I mean in the next topic, in machine learning, in the next class, right? So see you in the next video. Have a nice day.